A very good afternoon. Respected resource person for this session, Dr. Haranath sir, and dear participants. Today, we have a very eminent personality, Dr. Haranath sir from National Institute of Technology, Warangal, to deliver a talk on photoluminescence spectroscopy. In this AICT Training and Learning Atal Academy sponsored 1 week online faculty development program on photonics, organized by Department of Physics, Electronics and Photonics, Rajarshi Shahu Mahavidyalaya, Latur. I welcome you all for this session and request my departmental colleague, Mr. Swapnil Undalkar, to introduce today's resource person, Dr. D. Haranath sir. Swapnil, please.
Thank you, sir. If something is scattered with a lot of small things, they are spread all over it. Good noon to all. It gives me great pleasure to introduce a resource person of this session. On the behalf of Rajesh Shahu Mahavidyalaya, Latur, sir, I welcome you for this 1 week online faculty development program on photonics. Sir, you hardly need an introduction. You have made all of us proud by your distinguished work in numerous capacities. A man of distinct vision and a fountainhead of illuminating ideas, an idol of knowledge, experience, and inspiration, Dr. Haranath sir. Dr. Haranath sir is currently working as an associate professor in physics at National Institute of Technology, Warangal, India. Earlier to that, he served as a principal scientist at CSIR National Physical Laboratory, New Delhi for 20 years. He is a recipient of many awards and honors in physical science, including NPL's Young Scientist Award in 2003, CSR Young Scientist Award in 2004, DST's Boys Cast Fellow Award in Physical Sciences in 2006, Vera Distinguished Scientist of the Year 2016, Fellow of Luminescence Society of India 2017, Academic Audit Member of VNIT Nagpur 2017, Transfer of Technology Award 2018, Fellow of Luminescence Society of India 2018, Visiting Scientist for Nanotheronautics, United States of America 2019 to 2024, Grassroots Innovators, Virtual Mela Award 2020, etc. Recently, with the support of Professor D. Dhanakar, HOD Physics, National Institute of Technology, Warangal, he has developed an unique virus disinfectant system called All-in-One Ozonet, which can kill all types of viruses without involvement of hazardous chemicals within few minutes. This was well appreciated by Ministry of Electronics and IT, Government of India. His postdoctoral experience gained at Nanocrystal Technology, New York, United States of America for many years, and thereafter visits as visiting scientist had enriched him for the synthesis and characterization of binary and ternary nanophosphors for white light emitting diode applications. While at CSR NPL, he actively led the Alternative of Energy Materials group with an aim of developing novel nanophosphorus system and devices for various strategies applications. He had licensed a yellow-green emitting afterglow phosphor material in September 2016 to an Indian paint industry called MS Cutline Infra Products Private Limited, Nagpur for RS 11.50 lakhs. Before to that, he and his team of scientists had the credit of transferring 2 more technologies to Defense Laboratory Jodhpur DRDO and 1 technology of AC driven electroluminescent panels to ISRO. His other research and development development interests are positioned in the synthesis and characterization of nano-phase luminescent materials for LEDs and spectral energy conversion in silicon solar cells. Fabrication of electroluminescent panels for backlighting of LCD panels, development of primary colors, red, green, and blue, emitting long persistent phosphors for dark vision display applications, development of radioluminescent screens for high energy, up to 80 million electron volt, X-ray real-time imaging and biomedical applications of nanophosphorus as well. He has a vast research experience of 26 years and supervised 6 PhD, 2 MPhil, and 25 MTech theses. Dear participant, I wish to highlight that he has 6 granted patents, 3 field patents, and 13 chapters in books, more than 180 research papers in Science Citation Index journals of repute, 25 virtual journal papers, more than 200 national and international conference papers, 3 journal articles, 2 technical reports to his credit. Many of his research papers were cited by Nature, appreciated by Nanotech Web, verticalnews.com, highlybeam.com, etc. He is also an editorial board member for International Journal of Luminescence and Applications and reviewer to many international journals like RAC, APS, AIP, Willy, IOP, Springers, Elsewhere Sciences. His research credentials as reported by Google Scholar are H-index 37, ITIN index 100, citations 4,523. He has handled more than 3 crores worth of sponsored research projects sponsored by SERB DST, DAEB-RNS, DRDO, CSR, and MHRD. With the support of his colleague, he and Dr. Abul Azim together defended before the committee and successful in bringing DST FIST project worth rupees 2,075 crores to the physics department, NIT Warangal, for the procurement of XRD FESM machines. I welcome you to this session, sir. Over to you, Yadav, sir.
Please, sir.
Good morning,
I will.
everyone.
You can share, sir, now.
Okay, sir. Good morning, everyone. Thank you, Yadavji. Thank you, Swapnilji, for giving me a great introduction. So let me share my screen. Could you able to see my screen, sir? Yadavji? Is my screen visible?
Yes, yes. Yes, sir. Yes, sir. Yes, sir.
Okay.
Perfect.
Okay, right.
Fine,
Thank
sir.
you very much.
Okay, sir. Thank you.
So, good morning, everyone. I'm Dr. D. Haranath, currently working as Associate Professor in the Department of Physics, NIT Warangal. So my most of the research work is concentrated in the photoluminescence spectroscopy. So this is the topic I have chosen, and this is my email, and this is my research papers where you can see the type of research we are doing. And this is my host institute, NIT Warangal, and this is the institute website. This is our department's website, and below one is my profile and my research interests. So you can go to this website and you can see the research activities at NIT Warangal. And here at NIT Warangal, I have a very small group. Earlier to that, I worked in CSR NPL. There I was heading about 18 scientists. and 25 research students under my group. But now I have moved to NIT Warangal in 2018. Slowly, I am building my own group here, which is called Luminescent Materials and Devices Group. Currently, I have 3 PhD students. Naina is still working in NPL. And under the joint supervision of Dr. Sailesh. So she's about to complete her PhD. And Mr. Seju Mishra is currently working with me as JRF, and Ms. Rakshita also as a JRF, CSR JRF. She is working with me. And I have got 3 more postdocs in my group. Dr. Chandrarao, Dr. Vishnu Jaishwal, and Dr. Jayanti, and she is the woman scientist recently joined with me. So this is my small group. So all the research credentials goes to my past students and my present students. I'm just representing them, their work. So today's topic is photoluminescence spectroscopy. Let me touch upon a little bit of theory, measurement techniques, and some applications, some unusual applications I would like to show you, so that you may be triggered to do research in this very beautiful field of spectroscopy. So the first of the thing is, before going into the spectroscopic aspects or photoluminescence aspects, we should understand about electromagnetic radiation. You know that electromagnetic radiation consists of packets of energies, which are called photons, and you know that the electric and magnetic fields will be perpendicular to each other, and they will be oscillating and during the propagation of radiation. And if you see the electromagnetic spectrum, it ranges from shorter wavelength to longer wavelength. The shortest of all wavelengths is gamma rays. Okay, very short wavelength. And then X-rays, and then a small portion is our ultraviolet and visible. Visible, you know that violet to red, VIBGR. So this is a very small region, and infrared, microwave, and radio waves. So this is about increasing wavelength, and this is with respect to increasing frequency. So now we are concentrating a bit of ultraviolet. Maybe you can say that only visible spectrum, which is a very small segment of electromagnetic spectrum, which we are going to study. Again, in this ultraviolet, because earlier photoluminescence spectroscopy means it is the only visible light. The emission, if the material emits visible light, so within from violet to red, then it is considered as photoluminescence. But nowadays, a bit of ultraviolet is also taken into consideration. So you can see that the same this portion is enlarged here. So you have ultraviolet spectrum and visible spectrum. Visible start from 400 to 700 nanometers, whereas below 400 nanometers is ultraviolet. So you have ultraviolet A, ultraviolet B, and then ultraviolet C. And below 100 nanometers, below 200 nanometers, you can also call it as vacuum ultraviolet. You can call it as vacuum ultraviolet. So here it was not mentioned, but the thing is, you might have observed that if somebody goes into hot sun, so they say that your skin is burning, or you tanning of skin. It becomes little darkish, like southern part of India or Sri Lankans. You see that they are more towards equator and more sunlight is there. So they are having little less complexion. I mean, the dark complexion is more. So that is because of this sunburn or aging effect due to ultraviolet radiation, which is there in the sunlight. So that's why eventually, if you are too much exposed to ultraviolet radiations, there could be some DNA damages or cell damages that may occur. So that's why whenever you are going out, you are asked to apply sunscreen lotions. A lot of lotions are available in the market. So you need to put those lotions maybe to the face or hands and legs, which is being exposed to sunlight. So that is not that they will stop tanning, but the main purpose of applying those creams like Fair and Lovely, now it is called Glow and Lovely, and some sunscreen lotions. Actually, it has got zinc oxide or TiO2 based paste. Okay, so zinc oxide or TiO2 both have a similar band gap. So the band gap lies exactly in this region, UVA region. Okay, around 370 to 390 nanometers. So the bulk band gap. So if the band gap is there, that means this radiation can be easily absorbed. So the cream, if it has zinc oxide or TiO2, so that will absorb that radiation effectively, and that will emit in the blue region, somewhat bluish region. That is actually photoluminescence property which we are seeing. So that's why whenever you are going out, if you apply those creams, then instead of directly ultraviolet damaging your skin, so it will be absorbed by the paste you apply on your face, that cream, whatever you apply on your face. So that will absorb, and once you come home and wash your face, then everything will be washed away, and you may feel that you are little bit fairer than earlier, but nothing. Only thing is there are the radiation effects of sun is being not there. That's why whatever color you have, that is retained. You never become fairer. Okay, all these are publicity stunts, so don't believe that. Whatever complexion you have, that will be retained. You will not become more and more dark. So when you apply those creams, that's why when you are going out, you better apply certain sunscreen lotions. Okay, so that will block both UVA and UVB. And you may be like some of the TV advertisements you might have seen, that earlier in good olden days surf advertisement was there. So if you say that uh, uh, uski sadi meri sadi se safed kaise or something, some advertisement was there. So some two women, they cross each other, and the other lady will be wearing a brighter white cloth sari, whereas this one will be amazing to see. This lady thinks that how come that sari is more brighter than mine. So actually that's the advertisement of surf. Surf essentially they use a chemical called tinopol. It's a UV sensitive material. They mix it up with this one. Nowadays everybody is using, even these Rin and Tide and other people also, they are mixing. So that is a photosensitive organic fluorescent material. So what it does, that also absorbs the ultraviolet radiation that is present in the sun, and it converts into blue light. That's why whenever you whenever you wash your cloth with such type of powder, see, this tinopol will get into the fiber and it will stick to the cloth fiber. It's not a hazardous chemical. It's a very mild chemical. So that will attach to the fiber of your cloth. So when that is cloth is put under sun, so then you will see that it is looking very bright. It is emitting light. Whereas the same cloth, if you bring it to the shade, so you don't see that much brightness. That is just because of effect of tinopol, not that the cleaning is too much done for the cloth or something. Okay, so these are the business tactics they use. And UVC is you don't get it in the sun's atmosphere. I mean, in the Earth's atmosphere, the ozone layer which is there on the top, in the above the atmosphere, that will absorb the radiations. But if somebody like in spacecraft, if they are going above, so then there are chances the astronauts and other things, they may be exposed to UVC radiation, which are still dangerous. As the number goes, like UVA is little dangerous. UVB, it is more dangerous, and UVC is still more, and vacuum ultraviolet VUV is still dangerous. Okay, but vacuum ultraviolet and UVC are being absorbed by ozone layer, so we don't have much problem with this. So coming back to the visible spectrum, it starts from 400 to 700 nanometers. So this spectrum is very much useful for our I mean the living organisms, plants, and everything. Because you see, there is a standard called PPIX. PPIX is protoporphyrin 9. It's not IX, PP9. So this is an organic compound, which is which basically stimulates and for the development of hemoglobin in humans and chlorophyll in plants. Okay, photosynthesis and other things, they takes place with the visible light itself. So this is much more useful for our planet Earth, for plants, for human beings, for all animals, and so on. So this is one of the chemical we can use it as a standard, and we can estimate how better we are getting these radiations on Earth. So this is about light. Okay, so there are many spectroscopic techniques like gamma ray emission spectroscopy, X-ray absorption emission, fluorescence and diffraction spectroscopy, vacuum ultraviolet absorption. So many, Raman scattering, microwave absorption, SPR, okay, NMR. So there are many spectroscopic techniques, and their range of wavelengths are different, and their applications are also very different. So out of which we are going to talk about photoluminescence spectroscopy. So kindly mute your mic, all participants. Okay. So the energy units for this electromagnetic waves, you can write it as E is equal to h nu, or is it nu is equal to c by lambda. So c, it should be capital C. It is capital H c, small h capital C by lambda, h c by lambda. This equation, you know, h is Planck's constant and lambda is the wavelength of light, which we are considering. So only this lambda is variable here. These two are constants. So if you substitute these things, and from wavelength to energy, energy to wavelength, you can easily convert it. Okay. So if you want to characterize any material, if you try to make some material, so and if you want to study its structure, properties, or many other things, there are many characterization techniques are available. Both microscopy and spectroscopy. There are two different techniques that are available. Microscopy, basically, it gives information about the structure, morphology. Okay, and sometimes the microscopy can tell you the composition that is available with that one. Morphology, basically how it looks in minute scale. So those things, and there are many techniques like optical microscope, SM, TEM, IFM, FIM, STM, XRD, XRT, okay, atomic force microscope. So these are all the latest techniques that are available to in order to see the morphology, how they are looking at minute scale, and what could be their composition and other things, crystal structure, and using electron diffraction coupled with microscopy, you can study all these things. But spectroscopy is a technique where you can know the chemical composition, exact chemical composition. Even if one of the components lies in parts per million, parts per billion, very less. Even you don't know that much is present there or not. So that much of thing also can easily be detected using spectroscopic techniques. And if there is a slight variation in the composition, that also you can find it out. Of course, the crystal structure and the photoelastic electric properties of the materials and many other things, you can find it out because this is more sensitive technique, very sensitive, and good information you can get it with this. So as I told, along with the microscopy techniques and diffraction techniques, if you have this energy dispersive X-ray spectroscopy, wavelength dispersive X-ray spectroscopy, XRD, mass spectroscopy, SIMS, and time of flight SIMS, EELS, energy, electron energy loss spectroscopy. So there are many other spectroscopy. Few I have listed here. They are very important. And similarly, photoluminescence spectroscopy is also widely used by most of the material scientists. So for the optical spectroscopy, if you take a material and then some photons are put on that material, so what you can see is the scattering, that is called the Rayleigh scattering. You may get it, or you may get Raman scattering, or the photons may go through the material and transmission spectroscopy, or photoluminescence spectroscopy. There are different types of optical spectroscopies that are available, but we are talking about the fluorescence spectroscopy, which will be very interesting to see, because for other things you may have to have very sophisticated instrumentation. For this one, for most of the time your eyes are the detectors. You can see the photoluminescence with your naked eye. So once it is good, then you can go for the sophisticated instrumentation. So that's why this has got a lot of importance. And using spectroscopic techniques, so these are the various things you can detect. You can detect impurities, you can detect the dislocations, you can detect the defects, you can defect density, you can calculate, you can find out the structure of organic compounds. I'm not talking about the organic things now, only inorganic things I'm concentrating here in my talk. So qualitative and quantitative analysis you can do about the material. Chemical kinetics you can find it out. Sometimes you can find out the functional groups, like infrared spectroscopy. If you use not photoluminescence, if you use infrared spectroscopy, then you can find out the functional groups that are attached to that. So even the analysis of pharmaceutical drugs, where the composition can be, you can estimate it. So molecular weight also you can determine, and HPLC detection, high performance liquid chromatography also you can detect it. Band gap also you can calculate. So there are many things. So using photoluminescence spectroscopy, you may not have all these things. Most of the things can be calculated. But using other spectroscopic techniques, it's a general thing for all spectroscopic techniques. These are the many important applications or important findouts you can easily calculate it. Okay. So coming back to the photoluminescence spectroscopy, let me concentrate a small portion of spectroscopy. So as I told that a material, if it emits, it is the light which you are going to see. So what are the very fundamental processes to generate light? Can anybody tell me how to generate light? Very fundamental thing from the audience. Okay. So let me tell you, what is the general thing, like if you take a metal piece like iron and heat it for very high temperature, then the metal starts emitting light, isn't it? So that is the usual thing which we see. So that is called thermal radiation. If you heat a material to very high temperature, it starts emitting red light. And even if you increase the temperature of the metal, then it may start emitting blue light. From red, it will shift it to yellow, and then still it will shift it to blue or green, and then blue. So the energy of blue is much high. Means if you are providing more and more heat, your material will be, the metal will be showing that much light before melting. Okay. And the other process is luminescence. Okay. These are two different processes. And you may be thinking that what about radioactivity? Radioactivity, see here in this both processes 1 and 2, you are using some external source. Whether you are heating the material by providing heat, in luminescence you are providing some ultraviolet radiation or some radiation on the material which is emitting visible light. In both the cases you are getting visible light, but there is some external source. In radioactivity, It's an inherent thing. You don't no need to excite it. It's already emitting from its own. So radioactivity is not a luminescence process. Okay, and there's a degradation of the material, half-life and other things. But here we don't have such type of things. There is no degradation of material. So the ultimate source of light, it is sun. So what are the lighting technologies people have experienced? The first generation is fire. When man invented fire in long back, so that became as a source of light, and for moving in the night times, or to have his food burned on that one, cooked on that fire. So this was the first generation of lighting sources, and the second generation of lighting sources is incandescent lamp. So Thomas Alva Edison discovered this one in 1879. Accidentally, it was discovered, but later on, the incandescent lamps were replaced by mercury vapor lamps and sodium vapor lamps, which you use in our laboratory. Okay, so these are called second generation lamps. Third generation lamps are the fluorescent lamp, tube lights that we use in our household, and CFLs, compact fluorescent lamps, which were in 1997. So where low pressure mercury is being put in those lamps. Okay, so these were the things, and the fourth generation of that one is nothing but the light emitting diodes, solid state lighting or light emitting diodes, you can say. So these light emitting diodes, see, from first generation to fourth generation, if you see here, we are not concerned with light. So light is less, heat is more in first generation. In the second generation also, if you see, almost 10% light is there and 90% heat. The bulb, if you see, which you use in our uh, maybe in kitchen or bathrooms. So these incandescent lamp, they are very inexpensive, very cheap. You can have it in 10 rupees a bulb. So you see that light is less and more heat is generated. Okay, and so as you proceed further, the fluorescent lamps, they are more energy efficient compared to incandescent lamps. So fluorescent lamps, about 60% they give light, and 40% of heat and other forms of energy. We don't know what are those. So CFL is still better than fluorescent lamps. Okay, so now LED, when LED lighting, if you use the thing, about 85 to 95% of light we are getting out. The electrical to light energy conversion is about 90%. 85 to 95 percentage of that one will be light, and only 5 to 10% is the heat and other uh, things. So more and more light we are getting. So that's why government is also urging use to use these LED lights, because it is more energy efficient. Maybe a 12-watt bulb is equivalent to the fluorescent lamp of 40 watt. Okay, so that much light it can give. So they are more energy efficient, and life also, if you see from here to here, the life also has increased tremendously. Okay, so the same then why thermal radiation is not considered as photoluminescence? Because a metal is heated, it emits electromagnetic radiation. That's what the red hot iron, which I told. Okay, but one thing you need to remember, that if you are heating the metal to very high temperatures, then the color of the emission also is changing. Means the color of emission is directly proportional to the temperature you are providing. But in luminescence, in photoluminescence, it does not depend on temperature. There is like if you are giving excitation, the emission will be same. Even if you increase the flux of excitation, your emission will not change. And for example, for the same incandescent lamp, so we use tungsten as the metal in that. Is it not? So tungsten, why you use tungsten metal in the as a filament in the those lamps, incandescent lamps? Because tungsten has got the maximum melting point. The melting point of this tungsten filament, because a bulb operates at 3000 Kelvin, because vacuum will be there inside. At 3000 Kelvin, that is the temperature of the filament. So in order to sustain this much of high temperature, only tungsten we can use. Tungsten melting point is 3683 Kelvin, whereas the operating temperature is 3000. Okay, this is highest of all, among all metals. That's why we cannot use aluminum or copper or any other. So only tungsten is used because of high melting point. That's why if a high current passes through this bulb, it fuses. Means the temperature may go beyond the melting if a high current passes. That's why it breaks. Sometimes after usage, you see that suddenly the bulb, the filament breaks. That is because there is it might have reached beyond the melting point suddenly, so it has melted at that position. So it becomes, I mean, the filament breaks. So that's the reason. So that's why thermal radiation is not considered as luminescence. Okay. So because it is changing with the wavelength, changing with the temperature you provide. Then what is luminescence? Then the question comes, then how exactly we can understand what is this luminescence or photoluminescence? Luminescence is a process, non-thermal type of process. There is no heat generation in that. It's a cool process where you take a material and then shine some invisible radiations. For example, alpha, beta, gamma, ultraviolet. These are the wavelengths we cannot see. So if some invisible radiation falls on certain material and that material emits visible light which we can see. For example, this one. So this is an example of photoluminescence from minerals, rocks. If you go to seashore or river bank, you may get a lot of corals, small stones, colored stones, and other things. So those things, if you put under ultraviolet light, so sometimes they show a very beautiful color. These are the various you can see some collected from seashore. So many things, if even marbles also, sometimes pieces of marble, just put it. So some are glowing very bright red, bright green, okay, red, orange, yellow, many other things. Nothing has been done. Nature has done directly. Maybe due to volcano eruption, or maybe due to diffusion of various dopants, minerals that are present in the earth. So they have get into that rock, and the rocks are giving, when you put it under ultraviolet, 365 nanometers. So this is how it is glowing. Similarly, these are man-made synthesized materials in the laboratory. They are the standard materials which we use in televisions and tube lights and many other things. So these are the short names, like BAM is barium magnesium aluminate. Okay, so barium magnesium doped with manganese and so on. They are all commercial names, and under room light they look like this. This is the body color, and under ultraviolet, if you put it at ultraviolet, UVC, basically UVC 254 nanometers, you see this powder will glow violet, this is showing blue, this is showing green, yellow, dark yellow, orange, red. So all 7 colors people have made. This is artificially made. So this we are going to learn today. So how to make these type of materials. Okay. Don't be confused with the body color and the photoluminescence. Photoluminescence, you need to have ultraviolet light. If by shining ultraviolet light, if you see such colors, then that is photoluminescence. If you see under room light, it is only the body color. Okay. So how do you understand this phenomena? Like you are shining these materials, whether natural or man-made materials, with ultraviolet. This is blue line. So absorption takes place. The materials will absorb, and the electron goes to the higher energy state, and there are closely spaced energy levels. So electron slowly comes back to the lowest of the conduction band, and from where which drops. Okay, so that's why the ultraviolet energy is a higher energy radiation, whereas visible light is a low energy. Whatever we are getting is a lower energy compared to that. So this is the same you can understand, like you can give a lot of push to a person to get to the higher energy state, and he will step back to the lowest of the conduction band, and he's jumping back here. The energy is less. Okay, so where does the excess energy goes? This goes as phonons. Okay, lattice vibrations or something, it will be lost in that. So we need to understand the band gap of these materials. If you understand the band gap, then no need to give very high energy and pump it to a very high level of these electrons. You can pump it to the minimum level, and then you can get back the energy in different fashion. So this is how you can understand the luminescence process. And you know that you might have studied in your class 10th or during plus 2. So fluorescence and phosphorescence. Fluorescence is the process where the instantaneous emission, like if you are shining an ultraviolet light and immediately you are getting another wavelength, another visible wavelength coming back from the material, it is called fluorescence. And the time of duration is 10 power minus 8 seconds. Whereas phosphorescence is a delayed fluorescence. Delayed fluorescence means it takes time to come out, and then it stays for longer time. For example, if you are giving excitation energy to certain electrons, so it will absorb and it will go to the high energy state and relax back to the ground state. Okay, instantaneously the electron jumps to the valence band, then it's called fluorescence. But if it finds some other energy levels, maybe created by doping, or the material has some other energy levels close, which are close to the conduction band. So electron, instead of jumping that high, it will take this path and it will slowly come back to the lowest of these levels, and then it will come out. So this intersystem crossing will delay the emission. So that's why afterglow, or you can see the material glowing for longer time. So earlier it was few seconds, as per the definition, greater than 10 power minus 5 seconds to few seconds, it was called fluorescence. But now scientists have achieved very long fluorescence, that even days. Once the excitation is given, the phosphorescence goes for few days also. Okay, so we have been working on both type of materials, and here is just an example which I am showing it to you, that this is one of the quantum dots we have made using zinc sulfide doped with manganese. Here you see it's a fluorescent material. It looks very transparent like water under room light, but if I put it under ultraviolet lamp, so because of manganese, it emits red. Okay, this liquid emits red, and it's an instantaneous process. Just you remove it from the ultraviolet source, immediately it loses its emission. So it is the decay time is 10 power minus 8 seconds. It's an instantaneous process. Like here you can see that once it goes to the higher energy state, immediately the emission comes. Okay, whereas phosphorescence, it goes to the higher energy and it transfers intersystem crossing, and then it comes out. So this delays the process, and as I told, 10 power minus 5 seconds and above, it is called phosphorescence. And this is one of the paints we have developed at when I was working in NPL. So that was coated as a dial of a clock. So you can see in the night it glows, because in the daytime this is special material which we have coated. It doesn't require any ultraviolet light. You can just put it under sunlight or room light. It will absorb that one, and it has a very long emission, long duration of emission. Like it can glow around 12 hours. So throughout the night you can see the glow of this one, and you can know what is the time. Okay, the intensity will drop little by little. It won't maintain for 12 hours. It won't maintain the same brightness, but brightness will come down. But even then, you are able to see that. So these are the examples of that. So this is about a brief history of this phosphorus. Sometimes I am calling it as luminescent material, and sometimes I am calling it as phosphor. Okay, it is not phosphorus. Phosphorus is an element in the periodic table, atomic number 15. Okay, phosphorus is different and phosphor is different. Phosphorus is an element in the periodic table, whereas phosphor is a compound. Okay, but why similar name? Why can't we have a different thing? So there is a small story behind that. Ancient Greeks, when they were looking at sky and predicting many things, similarly they used to see some rocks. They were glowing in the dark. They thought it could be ore of phosphorus. So when it comes in contact with the moisture and air, oxygen, so those things may be burning. So that was the property of phosphorus. So they thought it is the burning of phosphorus. So later on they could see that every day it is glowing, and with time it is the intensity is decreasing, because if something is burning, it should not glow next day also, na? So they were confused, and they once again they started checking, and they thought it is radioactive, but it is not radioactive. Every day it is gaining the sunlight, and in the night it is glowing. The early time it was so bright, and after that it is decreasing intensity and so on. Then since they thought it is phosphorus, so they have cut short the name as phosphor. They have cut short the name phosphorus to phosphor, but phosphor is a compound. Phosphorus is a element in the period. Both are different. Okay, and in 19th century itself, Herschel, when he did some experiment related to this quinine solution. Okay, quinine is an organic compound in solution. So when he has kept, and when sunlight falls through this some filter blue glass that was there on the church, so out of all radiation, so it has it's like a band pass filter. It has emitted only blue light falling on this one. When this blue violet or blue ray felt on that one, then he could see different colors coming out of that wine glass. There was a wine glass also. Then he was looking this emission through this. This is another filter. So he could see that a lot of colors that are changing with wine and without that. And so then he could see that there is something like usually in sunlight or in normal light, quinine solution doesn't give fluorescence, but this having this ultraviolet or some blue light type of light, when it is falling, a lot of bright fluorescence is observed. So that was the first thing he could see it in 19th century. And as I told that before that itself, the Bologna stone, which is called barium sulfide. So this barium sulfide is the material which was glowing in the rocks. There could be some unintentional doping by nature itself, but these are the stones which are glowing in the night when these Greeks have seen. So it was first, it was observed in 1609, but the name was given by Weidmann in 1888. Okay, so after that, after barium sulfide, scientists started working on zinc sulfide, another sulfide material doped with copper. So with this one, people could achieve about 40 minutes of decay time. Here, few minutes only. So 40 minutes, and by adding a little bit of cobalt, again they could improve it to about 1 hour, 1 hour glow in the dark, completely dark. So this was the thing. So it was having a great advantage, these type of sulfides. After that, people started working on other sulfides like strontium sulfide, calcium sulfide, also bismuth sulfide. All sulfides they found. They thought all sulfides they have this type of characteristic, and they can emit. They are excitable by sunlight. That is the main advantage. They don't require any ultraviolet or any other external source. And but the main problem was they are chemically unstable, because sulfides, when they come in contact with moisture, it releases H2S gas, and then it will become oxide material. So this was the main instability feature was there with sulfides. So they thought it's only the sulfides which can go this type of things. And during Second World War, there was some other type of phosphors people have developed that is called photostimulated phosphors. So this is another interesting phosphor material. Like they made some phosphors and they coat it on white paper. It's looked like powder has been coated on that one. The beauty of these photostimulated phosphors is that one can write some message using some laser, and which will be stored. See, like you can write a secret message on that paper which is coated with this phosphor. So that message is stored, and again, if you send that information to the your boss or during the war time, that fellow used to put that sheet under ultraviolet of particular frequency, then he could read out what exactly matter was there. So it was like storage phosphor. It was storing that information, and again he could eliminate all the thing, and he can write another message and he can send it. Only the enemies, whoever gets that one, they think that it's a piece of paper, but it was the communication that people have done during that time. So that is called photostimulated phosphor. But after the Second World War, then the research also stopped. Then once again people got interest in this one with in 90s, when Matsuzawa, a famous scientist from Japan, he developed some oxide materials which can show this afterglow or phosphorescence property for more than 1 hour. Like green, it was about 10 hours, blue, it was 1 to 2 hours, and red is about 15 minutes of afterglow or phosphorescence time. So then people started thinking, oh, even the oxides also can show. They earlier they were thinking only sulfides can show, but oxides and other materials also. So then people started working with lot of rare earth materials and lot of oxide materials. Still people are working. And with the advent of this nanotechnology, when you make these particles in nano regime, some unusual properties people could see, and still the research is going very strong. Like for example, the quantum dots which I have shown you earlier slide. So it looks like water in usual case, but if you shine ultraviolet, it looks red. Okay, that is because of the quantum dot emission. So, and that will be very very strong, and the material that is there in that liquid is only few micrograms, even not a gram. It's micrograms of that one that is giving that much strong emission. So the usually these materials, whatever we make it oxide, sulfide, they are like powder materials. Okay, you can put it in some paint and then you can paint it on the wall or on the various substrates. But quantum dots, if you can make these materials in terms of quantum dots, then it will be transparent. You can coat it on any glass. You doesn't know that it is being coated with a phosphor, unless some ultraviolet light, if you shine, then automatically you can see the glow. Otherwise it looks like normal glass. So there are various advantages have come into picture. Okay, so depending upon the source of excitation, they are named in different types. Like photoluminescence, photo, as the name says, photon is light. So if you are using ultraviolet and if the emission is in the visible region, the emission means the color whatever we see. If you are shining ultraviolet and if you see the emission, that is called photoluminescence. Instead of photoluminescence, if you apply electric field, either AC or DC, okay, so then, like for example, your cell phones, there is a battery at the back. So when you switch on, then you see glow in that material. So that is called electroluminescence. This one, if it, that could be AC electroluminescence or DC electroluminescence. In cell phones, it is DC electroluminescence. So instead of electric field, if you are using electrons, like old type of TV sets or monitors, we used to have a bulkier thing. There is an electron gun at the back, old TVs also. Okay, so whatever glow you can see on the screen is called cathodoluminescence, because cathode rays, electrons are falling on the screen. And if X-rays are falling and if you see the visible luminescence, that is called X-ray luminescence. When you see ultrasound or something, then it is called sonoluminescence. When you use some solvents and photons, then it is called salvatoluminescence. And there is some chemiluminescence. Chemiluminescence is the one where see, you know about exothermic and endothermic reaction. Like exothermic, when you add two chemicals A and B, then if heat is generated, then you call that reaction as exothermic. And if it is cooled down, then it is called endothermic. Then that means heat is a form of energy. Instead of heat, why can't light can come out of that reaction? So there are certain reactions where light comes out. So that is called chemiluminescence. Okay. For example, chemiluminescence in the laboratory, you can make it, or I can tell you a simple example. I don't know what is being added in Mountain Dew, cool drink, Mountain Dew. If you take, so there is a slight yellowish color tinge is there in that. So that is some compound. What they exactly add, I don't know, but that is fluorescent. So that one, if you add a little bit of the household soda, जो खाने वाली सोडा होता है ना, so that soda, if you can add a little bit, a pinch of soda and hydrogen peroxide H2O2, hydrogen peroxide 2-3 मतलब 10 ml डाल देंगे in that bottle containing not a full bottle but half or very little of Mountain Dew, and if you can mix it up and switch off the lights, and you can see there's a beautiful glow, very bright glow. You can see that's a chemiluminescence. And sometimes you add more of baking soda, then gas may come out. So it is better that you remove the cap. Okay, of course, carbon dioxide also there in that cool drink. So this is small experiment one can do, and you can see this Mountain Dew experiment in YouTube also. You can see how beautifully people have done with that one. And bioluminescence is jugnu, the fireflies. So you might have seen in the fields sometimes in the night you see this jugnu, they emitting bright color for a few seconds, and then it will go off, and again it will glow, and so on. So that is a chemical which it secretes, like humans secrete sweat. They secrete a organic chemical called luciferin. Luciferin is an organic compound, but it is fluorescent. So what does the heat of the insect is taken as the excitation energy, and the jugnu will that heat from the body, it will go to the that chemical luciferin, and then it will glow. And once the body temperature goes down, it will disappear. And again, when because of flying, it gains heat energy, that body of that insect. So that energy is again transferred to that. That's why it is glowing and it is disappearing, and again it is glowing and again it is disappearing. So that is called bioluminescence. Okay, and some sea fungi also, some in some of the oceans, sometimes they see algae and other things. They are also showing a lot of bright blue luminescence. So that they are also bioluminescence, even in jellyfish and others. So they show glow. So that is also bioluminescence. So if you're using mechanical energy, and then if you see there is a glow, that is called triboluminescence or mechanoluminescence. So there are many types of sources. So if you use that one, and if you see the effect, the visible light coming out of that, then you can name that one. These are few things I have highlighted, but we are concentrating on photoluminescence for this lecture. So in my career, the both phosphors and nano phase of these materials, nano phosphors also I have developed, and many developmental projects were done with the DRDO. Basic research was done with the DST projects, and some exploratory novel type of taps and CSR taps and projects also I have developed. So there color TV, from color TV phosphors. When earlier there it was black and white TVs or monochrome TVs, you can call, because only single phosphor was coated. Later on color TV phosphors we have made, and long decay means long fluorescent, long afterglow. or you can say longest phosphorescent phosphors. So the called LD phosphors, we named it as LD. Gadolinium oxysulfide screens for X-ray phosphors. Electroluminescent lamp, I told but you know, this all smartphones, they have got very good displays, uh, multicolor displays. They are DC electroluminescent lamps, whereas we are developing AC electroluminescent lamps. Means that lamps does not have filament in that, so only you can plug it. So small A4 size paper sheet may be taking 1 watt of power, but you can see the illumination is quite high. So that is the futuristic lamps which we are developing, like quantum dots, nanocrystals, nanocomposites, bandgap engineering, novel nanophosphors. We are exploring some anti-reflection coatings, transparent oxides, hydrophobic materials. So many things we are working, and not only luminescence but other type of things also I am working. But let me concentrate more on this photoluminescent phosphor. These are the summary. What you can say, these are all materials developed by me. So these are the long afterglow materials which are glowing in the dark. Once the light is switched off, they are glowing in the dark. And these are red, blue, green, emitting phosphate nanophosphors. They are useful for biolabeling, biological applications. And this red, blue, green materials were developed for Nimitli project, and which were used in PDP TVs, plasma TVs. Of course, now plasma TVs were obsolete. LED TVs have come into picture, but for that reason, when the plasma TVs have come into the market, then at that time there was a lot of issues with the various colors, because plasma energy was quite high, so it was deteriorating blue and green. So we have solved that problem for that company called Samtel in Ghaziabad. So we worked with them, and we have given our material which they have put up in their TVs, television. So, and dilute magnetic semiconductors also we have studied. Quantum dot, we are the first to modulate color in zinc oxide quantum dots. Usually you type quantum dots in the Google, you may get cadmium selenide or cadmium sulfide, beautiful colored materials, is it not? But as for in zinc oxide, we could not reach red, but dark green to blue. So this was tuning for the first time. We have made it in 2008, and it was appreciated globally also. And not only this, making these materials at very small scale, we had a pilot plant where cages of phosphor material was made, and which the once we made this type of setup very big, which will cover the entire room. There was a staircase also to go to the top. So big stirrers, and the precipitates were getting in this bottom. This one, big bubblers, generator, many things were there. So this pilot plant finally we have transferred to ISRO, because they wanted to make the material in cages. Okay, way back in 2000 or 2001, we transferred this one. So phosphor nanowires also we have grown. We have made flexible and rigid type of electroluminescent AC electroluminescent panels. We have made it transferred to DRDO, and some blue and green emitting nanophosphors we have developed using combustion technique. And some phosphors we have been using for target drug delivery systems. Okay, put a magnet, and all the fluorescent material is collected at this one. It is both fluorescent and magnetic. So these are useful for target drug delivery systems. So that we have developed, and LEDs we have made. Okay, biological applications also we have studied, like core shell structures, tetrapods. And this is one of the interesting work which we did it in 2010, around 2010. So these were the culture plates of E. coli, control plates of E. coli bacteria. So most of the time, the nano materials, they say that they have got a lot of surface defects, and less of oxygen is present. So we have made zinc oxide quantum dots, and in that one we dipped the culture plate, and within few seconds you see the colonies have died. These colonies, where if the oxygen is there, then they multiply. They multiply into still bigger numbers, but it is dying means there is no oxygen present there. And if you increase the concentration of zinc oxide, all the colonies died. So the bacterial this in an indirect way of proving that zinc oxide have less of oxygen, more of zinc present in the that. So this was appreciated by nature also. And for solar cells also, we have made transparent, like this is a test tube having liquid with quantum dots of gadolinium vanadate, yttrium vanadate. So normally if you shine ultraviolet light, you see cone effect, cone type of spread of the light in the test tube. But here it is directly going through that one, illuminating the liquid. So that means straightway it is going, means this indicates that there is no scattering, means the particles are smaller than the wavelength of the incident light, means they are very small. So if they are small, they become transparent and the light can pass through that one without this cone type of effect. So that's the indication here. So this is the summary, whatever they have. Now let us understand how to make these type of materials in our laboratory. Okay, how we can easily determine this. So understanding these materials. So as I told that these fluorescent materials or luminescent materials, or in short it is called phosphor. Phosphor essentially has a host crystal. Any particular crystal you need to take, and some of the atoms, like this is the one of the atom, you replace it with another activator or luminescent center, which is the one which is emitting the color. Okay, so let us first understand what is a phosphor, then I'll tell you what lattices one has to choose and what ions we have to put so that we can get different colors. Okay, so a luminescent material will have a crystal, and some of the atoms are replaced by an activator or dopant is same. So this is the dopant which is placed here, and most 99% the host crystal itself acts as an absorber. When ultraviolet light absorb photon falls on that one, and it will transfer that energy to the activator, which will give the light. The excitation and de-excitation of this activator will give you the light for that material. But in 1 to 2% of crystals, they don't like to absorb. Then you need to add another activator or a sensitizer, it is called. It is like an antenna. It will absorb whatever light is falling on that one, and it will transfer this energy transfer. It will transfer that energy to the activator, which will show the light. Okay, so how do you understand this process? So from this is valence band, this is conduction band. If you are just taking a pure material and then if you are exciting with a certain ultraviolet energy, so electron goes to the high energy state and it comes back. So this is called band edge emission, because from band gap to band gap, okay, from the conduction band to the valence band, it is dropping. So it is called band edge emission or band gap emission. But in real sense, you don't find a perfect crystal like this. So you may have a crystal with an activator, some dopant or some defect level or trap level. Some levels should be there. So always they will take the shortest path. So electron jumps to this activator, or from it will go to the trap, and from trap it may come down, or from trap it goes to conduction band and it comes down. So these are various possible mechanisms that are available in luminescence. And once you get some luminescent material, so again there is another system called photometry and colorimetry. So with this one, you need to, this is only for visible light. So why this chromaticity diagram has been devised by the scientists? Because see, the color, if I ask what is the color of this one, you will say it is green. Okay, and if I ask the same, what is this color, say it is also green. You say it is dark green, here it is light green, but here this is also green. So there is a discrepancy in discussion. Like this color you say blue, and this color also you say blue, but there is a difference between these two colors, is it not? So they have devised a chromaticity diagram, and they have given different shades. Like this is called blue, this is greenish blue, bluish green, blue green, green, yellowish green, yellow green, yellow. So in common terminology, we loosely use light green or pale green or blue green, greenish blue. All have different meaning. Greenish blue, green blue, bluish green, green. They are all different. You see the color variation. So once you make the material, and if you plot a graph, spectral graph between intensity on y-axis versus wavelength, you'll get a spectrum. That spectral data, if you substitute in this photometry thing, then you will if the coordinates, if the coordinates lies in this region, then this you can call it as green. So whenever you are making such material, like Asian paints, if you go to Asian paints, there are a lot of shades they show. Okay, and there is some code given at the bottom. Similarly here also, whenever you make a phosphor, like green phosphor, you tell that it's a green phosphor having a color coordinates of x and y. You put this 0.2, you can say 0.2, and then 0.5 means somewhere here. You can put a dot, and you can say that these are the coordinates and the color is green. So this is a universally people will adopt that one. And of course the mixture of all the colors will give you white. And white also, the central white is perfect white or ideal white, and the white which is near to this corner is reddish, means white with little red rich, and here it is blue rich. Sometimes you go to a jewelry shop and you see that the light emitted by the lightings they use is white light, but it is more of yellow color, because they wanted to show the gold is glowing much more higher. So they prefer to take a bulb having white light, but the coordinate somewhere here, so near to yellow. सिमिलरली आजकल तो वो सब्जी सब्जी वाले के पास भी जाइए, मिर्च लेना है तो मिर्च के ऊपर ग्रीन कलर का लाइट डाला रहता है. So that is just to bluff you that it is more green or more blue or more yellow. So those are the things. So this is also very important in terms of photoluminescence spectroscopy. Okay. So one thing you need to remember that a material, whatever material you take, it should not be conductor, because conductor does not have a band gap. Okay, either semiconductor or insulator are good for our photoluminescence studies. So if you have a very small band gap, it's good, and if you have a larger band gap, it is still good. It's more good, because in a single lattice you can have different colors. For here you cannot have more number of acceptor donor pairs here. For example, here you can see, here if it is the band gap is very small, like semiconductor, you can have an acceptor level or a donor level, so the emission is fixed. Whereas in insulator, you can uh, you can vary the activator, like you can put manganese, you can put copper, aluminum, bismuth, many other. So each one will produce its own levels, not simultaneously. Means same band gap material, same host material you can take, and from that you can draw many colors. Whatever color you want, you can get it. So insulators are always good for us. The host should be having larger and larger band gap. For example, here I have taken zinc sulfide. So this zinc sulfide is having a band gap of 3.6 electron volt. So if I dope it with silver in that zinc sulfide doped with silver, I get blue emission. Blue zinc sulfide silver is blue. But instead of this one, if I don't take silver and if I put copper, I'll get red, green, very good green. Similarly, if I don't use copper or silver and use manganese, same zinc sulfide, earlier I have shown that it gives red color. That means host is same, But if you can play with the activators, you can have whatever color you want, you can get it out of all the visible light. So that is the beauty. So large band gap is always required. And this is some color wheel which I got it in the internet, which says that a material which absorbs violet light will give yellow emission, and the one which absorbs blue light will give orange emission, which absorbs green light will give red emission. Somehow it is true for all phosphors till now. If the absorption lies in the violet region, then that emits yellow. This is somebody has made this one, but it seems to be true for all phosphors till now. Okay. And now we could understand that the host should have larger and larger band gap, and insulators are better compared to semiconductors. Okay, that is one thing we have learned. Now, what should be the activators or luminescent ions? So luminescent ions, when you are doping that material or that dopant into that lattice, okay. So if, for example, manganese or antimony or cerium, europium, they get influenced by the lattice. Means lattice most of the time it will be inert. It will not take part any of the reaction. Just it will absorb the ultraviolet radiation and transfer it to the dopant. But in certain cases, the host will not sit idle. The host will say, no, I will also influence something. So host influence, and because of host influence, the manganese emission may change from green to red, green, orange, red. Okay, depending upon the host contribution. That's why here asterisk stars have been put, and here it is written. It is called crystal field splitting. Means crystal, the host crystal will have some influence, like Zeeman and Stark effect you might have studied. Zeeman effect is the influence of splitting of spectral lines in the presence of magnetic field. That is Zeeman effect. And in the presence of electric field, it is Stark effect. Is it not? So similarly here, if you are doping in certain crystals and the crystal is influencing its emission, then you can get different colors. Then that is called crystal field splitting. In very few ions, it will show like this, like antimony blue and cerium from UV to red, any color, depending upon the influence. More influence, more more towards red. Less influence towards left hand side, like that. But here you see there are other set of ions, okay, dopants. They never bother about crystal. Whatever crystal you dope it, they have fixed color, like tamarium. If you dope it in any number of any crystal you dope it, it will never get influenced by, it is very rigid. It will never get influenced by the crystal, and it will show its emission. That's it. Of course, the intensity may be little varied, a little less or little more. So, but they are fixed colors. They don't change with the crystal. Okay. And let me tell much more in detail about this one. And how much activator we need to put, that is another question. Like in a crystal, if you are adding an activator ion and it is substituting one of the sites, so slowly if I add more and more activator, and it will replace many of these sites, is it not? So how much I have to put? See, if you put very little, then the photoluminescence emission will be little bit weak. But if you start adding more and more activator, your spectrum will be much intensified. Okay. So and after a while, you see that the intensity again it is dropping down, even though you are increasing, because you see when this activator is emitting light, okay, visible light, it is absorbing ultraviolet and emitting visible light. When it is emitting visible light, the whole or the rest of the crystal will act as a transparent plastic type, transparent matrix. It will just allow the light to go out. That's why we are able to see that one. That's why you see here also one activator is that this will also absorb ultraviolet, and it will shine color for which the rest of the crystal will be transparent, and the light will come out and we can see. But if you add a lot of activator in a crystal, so what it will happen? So the one of this one is excited by the ultraviolet, and the emission is taken away by other nearby atoms, because these are not satisfied with the amount of excitation that it is getting. So the bouquet has some ions. So they try to take out the energy. They wanted to take out from the crystal and from the nearby atom. So the overall effect is the intensity again comes down. So there is some optimum condition, like little by little you have to add. You have to see that initially it is like this, then it is increased, then it is increased, then it is increased, then it finally increased, and after that when it start decreasing you have to stop it. Okay, so otherwise it is called concentration quenching. This quenching means losing. Okay, and this is an interesting periodic table of lighting elements. So this is in some of the journal I have taken, very beautiful thing for our photoluminescence study. So here you see that all the activator elements, they are marked green. So the activator elements are marked green. So they are good activators. And the purple color are good host elements. So these are good host elements. And here in some cases it is given both green and purple. So that indicates the titanium, vanadium, they can act as host as well as activator, depending upon the amount it is being present in that crystal. If it is very less, then it will act as activator. If it is more, it will act as a host. Okay, and the plasma elements, the yellow one are plasma elements. The discharge of these gases will give you the light. That's why you have sodium vapor lamp, mercury vapor lamp, sulfur vapor lamp, and all the noble gases like neon vapor lamp, argon, krypton, xenon vapor lamps, and the discharge of this one will give you the light. So these plasma elements we are not considering, only the host and the activator things. And interestingly, you see the actinides, all actinides are radioactive in nature. Uranium is the only one which gives the luminescence, but very rarely people use this one. And the lanthanides, all lanthanides, you see, they are good activators, except holmium and promethium. Holmium also people have studied. This is a very old photograph. Holmium, it gives in the infrared region. Okay, earlier by this time when this table was made, they might not have used, but holmium also gives emission. Promethium also people studied, but very rarely, because out of all these rare earth elements, promethium is the only poisonous compound. So this is very poisonous, like cyanide. So people or the guides are afraid of giving promethium related research to the students. So a little unknowingly, if it is touched to your hand and you have not washed properly and you had your food, then it will act as a poison and that may kill the student. So that's why very less research has been done on this one. Rest of the things are non-hazardous. And you see that the F block elements, except lutetium, all are good activators. So what do you understand by this? And one more thing, what you can see here, these are all transition metal ions, D block elements. D block elements and F block elements, they are good activators. That means when you see the electronic configuration, the nucleus is there, S shell, SPDF, SPDF. So the distance between S and P is not in visible region. P and D is not in visible region. D and F lies in the visible region. That means the D block elements, if you write the electronic configuration of that one, 3D, after 3D, what it comes is 4F, means D, after D it is 4F. So electron goes from 3D to 4F and comes back. So the distance between D and F lies in the visible region. That's why D block elements, when you use, you get visible light from the material. If you don't use D block, if you use S block or P block or something else, you may get it light, but you cannot see. That may be in ultraviolet or infrared or some other region. Okay, so D block elements are good. Similarly, F block elements, this first line, F block elements means after F, 4F, what is there? What is the next level? After 4F is 3D. Okay, so the distance between F and D or D and F is same. So that lies in the visible region. That's why all these rare earths are good activators in the visible region, and all these are magnetic in nature. So people have studied these things also nowadays. So you can take it as a in general case like transition metal ions and rare earth ions are good activators. So you have to choose from these two only so that you will get better visible emission. Okay. And lutetium has got all the 14 orbitals filled with electrons, F14. So it is completely filled. So it acts as more like a lattice, host lattice element, not as a activator. Except this one, all have less than 14, so they act as good activators. Okay. So now how to make this one? Now we could understand what is an activator, what to choose as an activator, and what to choose as a host. Okay, so if you can make powders and if you make phosphors in bulk size, means the size of the phosphor material is from 1 to 10 micrometers, you can call it as bulk phosphors. And if the size in nanometers, 1 to 100 nanometers, then you can call it as nano phosphors, the same material. And if it is still less, like 1 to 10 nanometers, you can call it as quantum dots and nanocrystals and so on. Whereas if it is 10 to 50 or 10 to 100, you can say, then you can have agglomerates. Agglomerates is a combination of various motichur laddu type ka. So you have all small things attached at single place. That's agglomerate. And if you want to know the much more details about various synthesis techniques, how you can use it in your laboratory, there is an article published in this materials science and engineering R reports. It was one report was written by my senior colleague, Dr. Harish Chandar. It's a single authored one. Synthesis development of nanophosphors. That was the title. You just type it. It's a free to download, and he has elaborated all synthesis techniques, whichever you like, you can use. Development of nanophosphors. And once you make that one, you need to sieve it. Channi leke sieve karna hai, so that big particles will be on the top and small will come down. So these things you can use it for certain application like paint or something. Gadolinium oxide, gadolinium oxysulfide, yttrium silicate, lanthanum phosphate, strontium aluminate, calcium titanate, yttrium aluminate oxide, which is also called YAG, barium magnesium aluminate, it is BAM, YbO4, vanadate, yttrium borate, and many others. And in all these cases, you can use either transition metal ions or rare earth ions, depending upon your choice. Okay, to get different colors. And this is a simple conventional method of preparation for the solid state reaction. Like you take powders of oxides and activator powder, you just take it, mill it, grind it in a pestle mortar. And if you want to mix it very well, you can add a little bit of solvent like alcohol or a little bit of acetone, you can put it and you can mix. This is only for better mixing. No need for the solvent. Dry mixing also you can do. Once you mix it, you pack it in alumina pots or graphite board, and high temperature treatment in a particular atmosphere you get the phosphor. This is the conventional phosphor preparation technique. Once the phosphor is made, it will be like a stone, piece of stone. Then again you have to grind it to powder, sieve it to remove bigger chunks, and the final powder you can use it for coating for various applications and so on. So this is the method of preparation of bulk material. For nano materials, there are many techniques. So why we should go for nano when bulk materials are good? The only thing is bulk, the efficiency, here you can see the efficiency, this is the luminescence efficiency. Efficiency of bulk is very good. Most of our displays we are using the same. When you are decreasing the size of these particles by grinding, then you are losing the this is the particle size. So you will be losing. But if you can make it in prepare the same in nano regime, then you can see the efficiency is much better than the bulk. Okay, the intensity may increase a lot. So there are certain evidences, and you can have transparency for these materials. So many other things will come into picture. That's why people go for this nano. And another interesting thing is, for example, here CDSE, the bulk band gap of CDSE is fixed. Whereas if you go to nano or quantum dot regime, the size determines the color. The smaller sizes will give you red emission, and bigger sizes will give you blue and green emissions, and so on. The size of the quantum dot, size of the agglomerate will determine the color. So here tunability will come into picture when you go to nano. Whereas in bulk, you have fixed color of emission. This I am not talking with respect to dopant. If you put a dopant, the dopant related fixed emission will give. But if you take pure cadmium selenide, here pure cadmium selenide has a fixed band gap, and whatever color it gives, that is fixed. Whereas in nano regime, the same cadmium selenide, you can have different color emissions from that. Okay, that's the beauty of that. And methodology what we adopt is both synthesis and evaluation techniques here. Synthesis, you can use chemical methods like precipitation methods, sol gel, combustion, Pechny, lyophilization, many other techniques you can use, whatever technique. And I'll tell you some of the simple techniques which we can use it in your laboratory. And evaluation and characterization. For evaluation, both compositional evaluation will do, and luminescence evaluation also will do. Compositional will go for XRD for structural determination, SEM, TEM for morphology determination, SIMS for elemental analysis, atomic absorption spectroscopy for elemental analysis. There are various things we go for the composition evaluation. Really, we got that material or not. And luminescence characterization like absorption, excitation, emission, decay time, brightness. So these are the things which we will carry out usually in our laboratory. So this is just a comparison between phosphor and nanophosphor. So I told that sometimes we get more and more efficient nanophosphors also. This I'm skipping this. So let me go to the instrumentation part. Like once you are able to successfully make such type of materials, what are the things how you can use an instrumentation techniques? Usually when you are want to record the spectrum of such luminescent material, two types of lamps are available. One is mercury vapor lamp, another one is xenon vapor lamp. But mostly xenon vapor lamp is being used in spectrometers, because mercury vapor lamp earlier they used to use, it's also a discharge lamp, but you see some of the wavelengths are missing. It starts from 200 to 700 nanometers and little bit of IR also. But you see some peaks are very strong, and suddenly it is dropping down to zero also here. Suppose your material absorbs in this region, and suppose if you calculate or if you measure the absorption of your material, whatever you have developed, that material as absorption lies around 495, and if you put it under this mercury lamp does not have that wavelength, so your material will not glow. Then you feel that you have your instrument is not working, or your sample is not good. Whereas if you see this xenon vapor lamp, it has a very broad spectrum, and you don't see any wavelength missing. Of course, there is a drop here, and again it has come back, and it is almost broad. So people go for this type of thing. So there is no sudden drop to zero. So xenon vapor lamps are always good. Or lasers, if you have lasers, excimer lasers or any other lasers also you can use it for photoluminescence technique. And photoluminescence technique, using a spectrometer, you can record excitation spectrum, emission spectrum, both fluorescence mode and phosphorescence mode, synchronous spectrum, low temperature spectrum, many other things can be done. Similarly, lifetime measurements, how much time the electron is sitting in the conduction band. Fluorescence, I told it is 10 power minus 8 seconds, and phosphorescence, it is more than 10 power minus 5 seconds, sometimes even hours, days, I told. So how to determine that lifetime? So that also, using time resolved photoluminescence spectroscopy, we can estimate the time of sitting of this electron in the higher energy state conduction band. So that also one can determine. So chemistry people, they use it for some other testing, like quenchometry, surfactant enhanced luminescence. Like if you have coating, surfactant coating on that one. So sensitized measurement, chemical derivatization, chromatographic, and many other things. For organic things, they use this one. And polarization measurements also, whether the light which is coming out from that material is polarized light or unpolarized light, whether it is a plane polarized, circularly polarized, or elliptically polarized light. All these things one can study with the same luminescence spectrometer. Okay, so simple arrangement is like you have a xenon source, and there will be excitation monochromator, or you can say wavelength selector, you can call, because all wavelengths are being given here. So it will select one particular wavelength to fall on the sample, which is kept at an angle of 45 degrees. Here it is, sample holder is at 90 degrees, but it will be kept like this, 45 degrees angle. So light will fall and it will reflect, and there is an emission monochromator where it will record that spectrum, and there is a detector and a PC will be there where you can see the spectrum. So two spectrometers are necessary, double beam spectrometers are necessary for photoluminescence characterization. Suppose you have only one monochromator, you don't have the other one, what then you can have a filter. You can use a source and use a filter. So filter will pass only particular wavelength that will fall on the sample, but one spectrometer is minimum requirement for photoluminescence study. So this is a various other way of showing these things. So fluorescence is often viewed at 90 degrees orientation. Okay, so xenon lamp is used. So these are the various other ways of showing. The sample can be thin film, solid sample, pellet, or liquid also. Okay, so many wavelengths are falling on this monochromator, and one wavelength it is selecting and it is falling, which is called the excitation wavelength. So lambda EX, that will fall on the sample, then the sample will glow with maximum intensity. So that will be recorded by the emission monochromator and the detector. Okay. And instead of this arrangement, if you use gratings and mirrors, then it's called fluorimetry, luminescence fluorimetry. Both are same, whether you use prisms or gratings, it is same. Okay, so in the instrumentation, as I told, you can use xenon lamp or you can use lasers, and these were the two models which we were having at NPL. So Edinburgh spectrofluorometer, where grating and mirrors were used, and the other one Perkinamar luminescence spectrometer. So these two we were using. This has a time resolved capacity also. So decay time, how much the time the electron is sitting in the conduction band, or the defect levels, that also we can determine. So this is for simple photoluminescence spectroscopy. So luminescence spectroscopy, I told it's a very sensitive and selective method, and detection limits are in ppm and ppb levels. Intentionally and unintentionally, some atoms are present in that one, that also it will detect and it will show it. So all these types of spectrums can be recorded: emission, excitation, synchronous, fluorescence, and so on. So here is a summary. What you can see, the characteristics of photoluminescence frequencies. You can have many frequencies, which this many peaks. If it comes, then you can estimate the composition, because of what what is present, what peak you are going to get. And the width of this or the shift of this peak will tell you the stress and strain that is present in the material, and polarization of that one will give the symmetry and orientation of the crystal. Width of the peak, width of the spectrum will give the quality of the spectrum. Means if the width is large, then it is, you cannot say it is a monochromatic or pure color that is emitting from the sample. So it will be the sharper, then the color purity will be determined, and the height of the peak will give you the amount of material that is present, or amount of real quantum efficiency, or the best material you are going to make. So here you will have an absorption spectrum, also called excitation spectrum, and this is the emission spectrum. Okay, so the distance between the peaks of this one is known as torque shift. So this is how generally it is the and one thing you need to remember, that any wavelength you take it from this, of course we take the most excited peak wavelength for measuring the photoluminescence, but even instead of this one, if you take this wavelength also, if this wavelength is made to fall on the material, it will give the same peak but with less intensity. Maybe here it will have, because this intensity is less compared to this one, so this one may give peak like this, but the position will not change. Unlike in thermal radiation, the peak may change, the color of emission will change, but here color of emission should not change. That is the fundamental condition in photoluminescence. If somebody says that I have made material with tunable emissions, like you change the absorption and your emission is changing, then that's a CUDA material, that's a waste material, that's not a fluorescent material. Okay, there are many papers you can see in the internet also, that I have got a tunable emission, like you change the wavelength. If everything is changing, your emission is changing, that means you are not made very good material. Okay, the emission should not change, the excitation may change, the wavelength you can change, but for every wavelength the intensity may vary, but the position should remain the same. That is the first and foremost condition for photoluminescence. Okay, so these are some organic materials which they use it for standardization when you purchase any spectrometer. So they give this type of standards, you can use it. Okay, and I'm just switching what are the factors that are responsible for this. For the earlier, like temperature effect will be there, pH effect, if these liquids, filter effects, and all these things you need to take care when you are recording this one. So colorimetric diagram. So earlier I told that green, bluish green, blue green, yellowish green, they are all different. So how to determine this one? Using photoluminescence spectrum. So I have taken a small example. This is the photoluminescence spectrum of tube light. So it covers from 400 to 700. So all white light, all wavelengths are present. So this gives this illuminate to be white light. So some typical household uh, uh, spectrum I have taken, and we have to normalize it to 100%. That is 1. We have to normalize it to 1. The highest peak will be 1, and accordingly the intensity numbers will change for the all wavelengths. So here a difference of 20 nanometers I have taken from 400 to 700. So 400, 420, 440 nanometers. Okay, so for every this thing, so what is the intensity? This 5 lambda is the intensity. The 400, this is the intensity value, because you see around 450, after 450, 460 or so, you have the peak. So here you see 460 is 0.998, maybe 461 or 462, it is 1. So normalized to 1, this peak. So 1, and all will be lesser than that one. Okay, so everything is intensity values is put here, and if you take any standard book related to colorimetry, then for each wavelength they have got some standard values. that it is indicate standard X and standard Y values. They put it as a like logarithmic chart. They put it at the end in a book. So that is called X lambda and Y lambda. And of course, Z direction we are not taking, but Z lambda also. So that X lambda is multiplied with this intensity, then it's called X lambda, phi lambda. And if the Y coordinate is multiplied with this one, you will get this. Z coordinate multiplied with this one, this. And here blanks means 0. So after that, this is one of the famous methods called equidistant wavelength method of finding these coordinates. But there are many other methods also available. So if you take the summation of this one, it is treated as capital X. The summation of this one, just addition of this one, it is Y. The addition of this one is give Z. So X total is X plus Y plus Z is something else. So the X coordinate, the here, suppose this is the coordinate, X coordinate is capital X divided by X plus Y plus Z. So just determine that 0.29. And Y is equal to capital Y by X plus Y plus Z. It is this 0.34. Z anyway we don't have, but you can calculate. Of course, this small x, small y, small z values, if you add, then that will be 1 once again. So forget about this z value, 0.29 and 0.34. So x-axis 0.29 and 0.34. So if you see exactly, and you can put a dot. So this is the, it is not ideal white, it is towards little bit of towards green side. Of course, it is falling in the red, white region, so it is white light only, but it has a little green, more component of green is present in this one. Anyway, so this one, like if I want to sell this lamp, then I'll say that it gives white light with coordinates xy is equal to 0.29, 0.34. Like that, if I say in the international market, then they will understand, okay, this is giving somewhere here. So if the same thing, if you want to sell it to a jewelry person, he will not take, because he prefers the dot to be present somewhere here, near to yellow. Is it not? Okay, so that's the indication of this one. That's why you can calculate. Nowadays, see some CIE colorimetric color coordinates can be determined using some simple softwares also available in the net. You can search it out and you can put this PL data, photoluminescence data in that one. Then it will directly give out the calculated values of X and Y. So that also people are using nowadays. So time resolved spectroscopy, as I told, that it gives the lifetime measurement. So how much time the electron is resting in the higher energy state. Using liquids also you can determine. And the other way is quantum yield or quantum efficiency. Okay, some known material you have to take. So it has a quantum efficiency of 0.9, which is very good. 0.9 is 90%. So if you measure the quantum efficiency using this one, and again replace that one with your phosphor, and then you see, and then correlate that. So quantum efficiency is number of photons emitted to the number of photons absorbed. So how do you count the number of photons? So there will be a photon counting system attached to the spectrometer. So when you shine light through the from the source to that, so it will count number of photons. The counter will count. So number of photons that are coming in and falling into the material. And when the material is emitting, again there will be a photon counting system before the detector. So it will count. So number of photons emitted or to the number of photons absorbed. That gives you the quantum efficiency. So there is no phosphor with 100% quantum efficiency, but it is near to 1. Like here it is 90% or something. So here we can determine. So little more, maybe another 5 minutes I will take just to show you some beautiful applications of these luminescent materials. So luminescent materials, here few applications I have highlighted, that fluorescent lamps, the white powder coating which is there in the CFL and tube lights. So they are phosphor materials only. The red, blue, green coatings that are there in plasma TVs, that is phosphor. To improve the solar cell efficiency, you can have some transparent coatings, that is nanophosphor. luminous paints that glow in the dark. So they are also phosphor materials. CRT, cathode ray displays, earlier displays. Nowadays, nobody is using this type of thing. Electron gun and everything is there. So that is also a display. Solid state lighting is LEDs, where that light is emitted from the blue chip, and yellow phosphor is kept. So you are getting white light. And field emission TVs. So these are the future foldable TVs or very thin TVs, and biomedical applications like target drug delivery system, many other things. So some of my students are working, they have worked in this type of systems, and some people, they have submitted their thesis, and some are still working. So there are various applications that are there. Let me show you how this is good for white LED. So you know that all the three colors, primary colors, will give you white light, but you know that we have got very good blue LED, and if you diagonally, you see here yellow. So yellow phosphor, if you have, and if you put that yellow phosphor on blue LED chip, then you'll get white light. Okay, so white light, like here blue chip and yellow phosphor has been put in here, so you will get white light. But only the problem with this white light is it has blue component and it has got a green component, but there is less of red component. That's why you don't feel like studying under this LED lighting. Suppose if you put LED lighting in your house, and if you feel that something is missing, that is the red portion is missing. That's why people are working to develop newer and newer red materials. The problem is not with the red material, but that the red material should absorb blue light, not ultraviolet. So that is the important thing one has to do. So if you can do that one, then we can have better and better pictures on, and people will be happy to have those type of lighting in their houses. Okay, there are various LEDs which we have developed in our laboratory, like coated on white plate and glass plate, and put it on LED chip and so on. Okay, see, other important application is solar cell efficiency. We have got solar cell. We are not changing the structure of solar cells. The same solar cell, whatever you want, you can take it. But you see this gray portion is this portion is the actual solar light, sunlight, and our solar cell works in this region only. Mostly around 900 nanometers or little IR region. Our crystalline silicon solar cell has maximum efficiency, and this efficiency or ultraviolet and everything is wasted. So our phosphor materials will absorb ultraviolet and make it into visible light. So what we are doing is we are making a transparent coating, and we are coating that material on the silicon solar cell. Then what it will happen? So whatever ultraviolet light from the sunlight it is falling on that will be converted to visible light or IR light, where the efficiency is maximum. The same solar cell will perform very much bright. The electron hole pairs will be too much, and then we get more photocurrent coming out of that. So that is the idea with which our students are working. Because you see, there is an article in Times of India in 2010 or so. So this shows that after the tsunami effects, the Japan, they have started to build a very big solar station on moon, because on moon you can get 24/7 sunlight. So all that electricity, that sunlight is being converted into radio frequency lasers, and that lasers are being sent to Japan, where that is converted again to electricity, and that will be supplied to the various things. So they have envisaged this project by 2030 they are going to finish it. So they are utilizing this one, even though they don't have power cut there in Japan, but still they are thinking ahead. We should also think in that direction. We also worked in that direction. We have made certain transparent materials which can be coated on solar cells, because if it is a powder thing, then the actual sunlight will not go and your solar cell will not work. There should be a transparent cover plate, transparent glass plate with this nanophosphor coating, so that the efficiency will increase a lot. So this is what we have seen. This the photoluminescence spectrum. We can see this is the original spectrum. By putting such type of coated screen, then the efficiency increased, and this was appreciated by nature also, that we are doing wonderful work in that one. And there are some upconversion phosphors also we are working, like using lasers, core shell structures. Core shell means like center there is another material, and as a core and shell type of thing. So it will absorb and it will create a visible light coming out of that one. So that also we have initiated. And the earlier TVs are like this. Now future TVs are like carbon nanotube emitters will be put. The spacing will be in microns, and special phosphors people are making. We are also making, so that this will be sealed in very thin type of thing. And we are going to make it flexible also, so that what happens if and everything will be under vacuum. This will be a foldable TVs, LCD TVs for future, very thin, maybe calendar TVs also you can call it. Just put a nail and then you can hang your TV there. So these are the things for which we are also working, and we are making different types of phosphors, and we are trying to consult the industries, those who can make such type of TVs. And quantum dots, they are all appreciated by various sources and various universities and abroad universities and nanotechnology websites. So all these things we are carrying it out. And another important application, this maybe you people also can think, is see, when this notebandi has come, most of this currency has disappeared. Okay, so that is because most of the higher currencies were duplicated. So these 2000 notes and all notes, including our 10 rupee notes, so they have got special phosphors that are being put on that one. Not only our Indian currency, all this is the British pound, this is the ruble, and many other currencies also. They use fluorescent inks. They just put it. They doesn't look in the normal light, but under ultraviolet lights are certain things. And dinar, they have got a very dots, specialized dots they have put it. So it is very difficult to duplicate that one. Okay, those things. So these, you know, that even though now our Indian currency is from Indian paper and Indian printing, after the Modi ji has announced that notebandi, and they have introduced a new currency with different sizes. Okay, so earlier to that one, we were importing the paper, we were importing the fluorescent inks, normal inks, because this paper is a special paper. You see how many times you can fold it and unfold it, it won't break. Whereas normal A4 size paper or any paper which you use in our notebook, so if you multiply, if you maybe 100 times, if you fold it, it will break it into pieces. But these things, they run for longer time. So special materials. So he has initiated, he has told many scientists to work on this paper. NCL Pune is working on this paper production. They successfully did it. These fluorescent materials, still they are importing from Germany. So all these currencies they are using. So if you can make quantum dots, highly emitting quantum dots, and if you can supply to Mint, Indian Mint, so then they can print it. But there are certain problems also, because they should not be washed away with water. They should not lose their fluorescence. So sometimes some currency notes are there in your pocket, and your wife might have put it your belongings into washing machine. So because of the caustic potash and other things, the fluorescence should not die. Not only that, sometimes you iron your notes. Okay, in that case also it should not diminish. So there are many other harsh tests one has to do before that to be used in any currency note, because even if you iron it, this fluorescence will not go. Whereas our phosphor, whatever you make it, if you iron it, then everything will go away. So if it can resist those conditions, then you will become a billionaire. Really, you one those who can make such type of any colored ink, so they can supply it to the whole world. Okay, in one or two companies, one is Germany and one is in Australia, they are making and they're supplying to whole world. We also tried one fluorescent ink with red color, but still that test we need to do it. In 2010 we did it, and it was appreciated by nature also. India also started working on such type of systems like that, and they appreciated our work. But the harsh test we could not perform it. We are still working with mint compound where they print the notes, but still now they are still importing the inks from abroad only. So this is one of the areas where you people can think and work in that direction. So sunlight sensitized, not only ultraviolet, but sunlight excitable materials also we have made, and we have used it for various applications. These are what do you call that, phosphorescent materials. Okay, they can use it on toys, Taj Mahal, structural damage, many other ornaments, signages, like you go this way, that way, arrow marks and fingerprints. Many other applications we have done, and we have made many other tools just to show that here is under light and under dark conditions they glow like this. And articles also, Taj Mahal, not exact original Taj Mahal, but is a monument, a small piece we have taken and then we have coated and could show the different colors in that. And even exit signages in NPL, National Physical Laboratory, we have replaced with our phosphor material. If there is a light at the back, if suddenly there is a power off, then this will glow and it will show the path. So these are the things we have been working. And last slide, we are also working on fluorescent and magnetic nanoparticles. What is the idea of having both the properties is, like, you can have a drug molecule or a medicine and a nanoparticle with this, and if the nanoparticle is coated with this drug, and with a small magnet you can tune it to the exact tumor site. Okay, so we have developed various these materials of various colors and we have tested. Let me show you a small animation thing, why this type of fluorescent and magnetic materials are very important. Suppose there is a solid tumor that is present near to liver or near to heart, you cannot directly inject it here, so you need to give an injection here. So for example, cancer therapy, cancer treatment, they give many medicines, and it will go from head to legs, and it will damage most of the kidneys, and sometimes the cancer patient, you can see that hair has been lost and their skin become pale and many other things. These are the side effects of the cancer drug. Only 5 to 10% of drug will go to the actual tumor site to kill this one, to kill the cancer cells, but 90% it is damaging the whole body. Can we have a system like you give an injection, put a magnet here, so that everything comes here without damaging, and you can give only 10% of injection only, not necessary to give that much. So here you see, then when the injection is given, it goes to the heart, and little will go to this one, and it will go to the other parts. Okay, so if uh, so if I put a magnetic field, highly concentrated magnetic field here, then the particles will be attracted by that magnetic field. So now magnetic field is applied, so all the materials will be accumulated there. So, and by flipping the magnetic field here, by if you are making it like north pole, south pole, north pole, south pole, like you are rotating it, then the from the particles, the medicine will be uh, like you take a metal piece and put up and down like this. Then after some time, you see that the metal piece will be broken into two pieces like that. Here also, the drug will be flushed out from these particles. So we are working on such type of systems, so that this is called target drug delivery system, without disturbing, without causing trouble to the other organs. So this type of medicine delivery is given, then with less dosage we can help the patient. So this type of work we are working with Einstein College of Medicine in New York, Bronx, along with Nanotheranostics, a small company which is there in New York. So we are associating with them to develop such type of thing. My thing is to develop these particles. Okay, and they are biodegradable particles. inorganic biodegradable particles, and the addition of the attaching the medicine and other things, the other people like the nano theranostics is doing, and the actual testing that Einstein College of Medicine, they are checking in some mice and other things. So nano 2010, we have seen some applications of this nano phosphor materials in paintings, coatings, pigments, medicines, and so on. Nano 2020, nano phosphor 2020, we have seen some bio sensors, functional materials, and drug delivery systems, and many other things. But nano 2030, we can see many materials related to nano and nano phosphor related sensors and electronics, displays, flexible displays, many other things may come up in next decade. So these are the things which we can estimate it. And my own research emphasis is on these materials, and these are the products which we have already developed, and these are the technologies our group has transferred to various companies. One is for this Getline Infra, is a private company, is a government company. This is Samtel is again private company. This go for government DRDO, for DRDO, Liquid Crystal Research Institute, and then ISRO, and then this is another private company. Once again, we have made one particles analyzer and supplied there, and phosphors for plasma display also we have given it to Samtel Ghaziabad. So depending upon the industry requirement, we work and then we try to deliver the products to them. So finally, I thank the principal and director of FDP, Dr. Madhav Devhane sir, and Dr. Abhijit Yadav sir, who requested me to deliver this talk. He's the coordinator. Sorry, the spelling is wrong here. Coordinator. So coordinator of this workshop, and all the participants who are patiently listening my talk for 2 hours in this FDP program on this photonics. And I also thank all the teaching and non-teaching staff who are associated for this program from this Rajashri Shahu Mahavidyalaya, Latur, Maharashtra state. Thank you very much. And this is our institute during the Independence Day celebrations. And this is my card. You can have my email and phone numbers here. You can contact me at any time. And thank you very much for your patient listening. And I am happy to answer a few questions if the audience have.
Yes. Thank you very much, sir. Thank you very much. Dear participants, the session is now open for discussion. I think Mayur has raised a hand. Mayur, ask your question briefly.
Hello, sir.
Hello, Mayur.
Which type of laser that can be used in the photoluminescence?
So that's a good question. Photoluminescence, basically, if you use ultraviolet laser, the 325 laser that is available, okay, in the market, 325 laser, 325 nanometers. So usually they use that type of laser, and sometimes they use blue lasers also. Some of the materials, if see, always you have to see that from left to right. If you are using ultraviolet, the emission will be from visible, in the visible region, from blue to red. Okay. If you are using a blue laser of 450 nanometers, then your emission will always come near red. Okay. So blue lasers also they use, but mostly 325 nanometer laser, ultraviolet laser. It is also called ultraviolet laser. That's what people use.
Thank you, sir.
Thank you.
Thank you very much.
Thank you.
Yes. Now I request one of my colleague, Mr. Maruti Kumbar sir, to propose vote of thanks.
Thank you, sir. It's an honor to have been asked to offer a vote of thanks on the occasion of Faculty Development Program. On the behalf of our college and the Department of Physics, Electronics and the Photonics, I am very heartily gratitude to eminent research person, Dr. D. Haranath sir, National Institute of Technology, Warangal, for sharing lot of information. We are really enlightened with your knowledge and the present, sir. This is one of the memorable session. Sir, you have given the information of the photoluminescence spectroscopy, how to generate the light, artificial lightning technology, fluorescence and the phosphorescence, story behind the phosphorus and the phosphorescence. Sir, then you have moved towards that instrumentation part and the applications of that special nanophosphorus. So thank you, sir, for your fruitful information. I extend the thanks to Honorable Dr. Abhijit Yadav, sir, as the young scientist and head of the Department of the Physics, Electronics and the Photonics and the coordinator of the FDP. I also want to thanks to heads of the various departments, faculty members, research scholars, and the students for attending and the kind operation in making the session successful. Finally, I would like to thank all my colleagues for to making the session successful. And so finally, thank you all for your kind attention. Thank you all. Thank you very much, sir.
Thank you, sir. Thank you very much.
Okay,
बहुत
sir.
बढ़िया हो गया.